transports heat by convection. 3. Evaporation is a cooling process. Water loses heat and cools by evaporation, but rock does not. Think of the consequences of the temperature difference between rock and water. On a hot summer day you may burn your feet walking across dry sand or rock, but the surface of a lake or ocean is never burning hot. Suppose that both the ocean and the adjacent coastline are at the same temperature in spring. As summer approaches, both land and sea receive equal amounts of solar energy. But the land becomes hotter, just as rock becomes hotter than water. Along the seacoast the cool sea moderates the temperature of the land. The interior of a continent is not cooled in this manner and is generally hotter than the coast. In winter, the opposite effect occurs, and inland areas are generally colder than the coastal regions. Thus, coastal areas are commonly cooler in summer and warmer in winter than continental interiors. The coldest temperatures recorded in the northern hemisphere occurred in central Siberia and not at the North Pole, because Siberia is landlocked, whereas the North Pole lies in the middle of the Arctic Ocean. In summer, however, Siberia is considerably warmer than the North Pole. In fact, the average temperature in some places in Siberia ranges from 50 degrees Celsius in winter to plus 20 degrees C in summer, the greatest range on Earth. Temperature changes with latitude and season temperature. Changes with latitude. The region near the equator is warm throughout the year, whereas polar regions are cold and icebound even in summer. To understand this temperature difference, consider first what happens if you hold a flashlight above a flat board. If the light is held directly overhead and the beam shines straight down, a small area is brightly lit. If the flashlight is held at an angle to the board, a larger area is illuminated. However, because the same amount of light is spread over a larger area, the intensity is reduced. Now consider what happens when the sun shines directly over the equator. The equator, analogous to the flat board under a direct light, receives the most concentrated radiation. The sun strikes the rest of the globe at an angle and thus radiation is less concentrated at higher latitudes. Because the equator receives the most concentrated solar energy, it is generally warm throughout the year. Average atmospheric temperature becomes progressively cooler poleward. But, as mentioned in the introduction to this chapter, the average temperature does not change steadily with latitude, because many other factors, such as winds, ocean currents, albedo, and proximity to the oceans, also affect atmospheric temperature in any given region. The seasons EARTHCIRCL EST-HISU-NINAPLNR orbit, WHILE simultaneously spinning on its axis. This axis is tilted at 23.5 degrees from a line drawn perpendicular to the orbital plane. Earth revolves around the Sun once a year. As shown in Figure 18.16, the North Pole tilts toward the Sun in summer and away from it in winter. June 21st is the summer solstice in the Northern Hemisphere because at this time, the North Pole leans the full 23.5 degrees toward the Sunday. As a result, sunlight strikes Earth from directly overhead at a latitude 23.5 degrees north of the equator. This latitude is called the Tropic of Cancer. If you stood on the Tropic of Cancer at noon on June 21st, you would cast no shadow. June is warm in the Northern Hemisphere for two reasons. When the sun is high in the sky, sunlight is more concentrated than it is in winter. When the North Pole is tilted toward the sun, it receives 24 hours of daylight. Polar regions are called lands of the midnight sun because the sun never sets in the summertime. Below the Arctic Circle, the sun sets in the summer, but the days are always longer than they are in winter. When it is summer in the Northern Hemisphere, the South Pole tilts away from the sun and thus the Southern Hemisphere receives low-intensity sunlight and has short days. June 21st is the first day of winter in the Southern Hemisphere. 6 months later, on December 21st or 22, the seasons are reversed. The North Pole tilts away from the sun, giving rise to the winter solstice in the Northern Hemisphere, while it is summer in the Southern Hemisphere. On this day, sunlight strikes Earth directly overhead at the Tropic of Capricorn, latitude 23.5 degrees south. At the North Pole, the sun never rises and it is continuously dark, while the South Pole is bathed in continuous daylight. On March 21st and September 22nd, Earth's axis lies at right angles to a line drawn between Earth and the Sun. As a result, the poles are not tilted toward or away from the Sun and the Sun shines directly overhead at the equator at noon. If you stand at the equator at noon on either of these two dates, you would cast no shadow. But north or south of the equator, a person casts a shadow even at noon. In the northern hemisphere, March 21st is the first day of spring and September 22nd is the first day of autumn, whereas the seasons are reversed in the southern hemisphere. On the first days of spring and autumn, every portion of the globe receives 12 hours of direct sunlight and 12 hours of darkness. For this reason, March 21st and September 22nd are called the equinoxes, meaning equal nights. All areas of the globe receive the same total number of hours of sunlight every year. The North Pole and South Pole receive direct sunlight in dramatic opposition, 6 months of continuous light and 6 months of continuous darkness, whereas at the equator, each day and night are close to 12 hours long throughout the year. Although the poles receive the same number of sunlight hours as do the equatorial regions, the sunlight reaches the poles at a much lower angle and therefore delivers much less total energy per unit of surface area. Temperature changes with geography even though all locations at a given latitude receive equal amounts of solar radiation. Some places have cooler climates than others at the same latitude. Figure 18.18 shows temperatures around Earth in January and in July. Lines called isotherms connect areas of the same average temperature. Note that the isotherms loop and dip across lines of latitude. For example, the January 0 degrees Celsius line runs through Seattle, Washington, DIP southward across the center of the United States, and then swings northward to northern Norway. Such variations occur with latitude because winds and ocean currents transport heat from one region of Earth to another. Other factors, discussed in section on energy storage and transfer, the driving mechanisms for weather and climate, include the different heat storage properties of oceans and continents, evaporative cooling of the oceans, and the latent heat of snow and ice. Altitude. Recall from Chapter 17 that at higher elevations in the troposphere, the atmosphere is thinner and absorbs less energy. In addition, lower parts of the troposphere have absorbed much of the heat radiating from Earth's surface. Mount Everest lies at 28 degrees north, about the same latitude as Tampa, Florida. Yet, at 8,000 meters, climbers on Everest wear heavy down clothing to keep from freezing to death, while during the same season sunbathers in Tampa lounge on the beach in bikinis. Ocean effects. Recall from section on energy storage and transfer, the driving mechanisms for weather and climate, that land heats more quickly in summer and cools more quickly in winter than ocean surfaces do. As a result, continental interiors show greater seasonal extremes of temperature than coastal regions. For example, San Francisco and St. Louis both lie at approximately 38 degrees latitude, but St. Louis is in the middle of the continent and San Francisco lies on the Pacific coast. On average, St. Louis is 9 degrees Celsius cooler in winter and 9 degrees Celsius warmer in summer than San Francisco. Ocean currents also play a major role in determining average temperature. Paris, France, lies at 48 degrees north latitude, north of the U.S. Canadian border on the other side of the Atlantic Ocean. Although winters are dark because the sun is low in the sky, the warm Gulf Stream carries enough heat northward, so the average minimum temperature in Paris in January is around 6 degrees Celsius, comfortably above freezing. St. John's, Newfoundland, is at about the same latitude but under the influence of the Labrador Current that flows from the North Pole. As a result, the average minimum January temperature in St. John's is around 3 degrees Celsius, considerably colder than it is in Paris. Wind direction. Winds carry heat from region to region just as ocean currents do. Vladivostok is a Russian city on the west coast of the Pacific Ocean at about 43 degrees north latitude. It has a near-Arctic climate with frigid winters and heavy snow. Forests are stunted by the cold, and trees are generally small. In comparison, Portland, Oregon, lies at 45 degrees north latitude on the east coast of the Pacific Ocean. Its temperate climate supports majestic cedar forests, and rain is more common than snow in winter. The main difference in this case is that Vladivostok is cooled by frigid Arctic winds from Siberia. Cloud cover and albedo. If you are sunbathing on the beach and a cloud passes in front of the sun, you feel a sudden cooling. During the day, clouds reflect sunlight and cool the surface. In contrast, clouds have the opposite effect and warm the surface during the night. Recall that after the sun sets, Earth cools because radiant heat from soil and rock escapes into the air. Clouds act as an insulating blanket by absorbing outgoing radiation and re-radiating some of it back downward. Thus, cloudy nights are generally warmer than clear nights. Because clouds cool Earth during the day and warm it at night, cloudy regions generally have a narrower daily temperature range than regions with predominantly blue sky and starry nights. Snow also plays a major role in affecting regional temperature. Imagine that it is raining and the temperature is 0.5 degrees Celsius, or just above freezing. After the rain stops, the sun comes out. The bare ground absorbs solar radiation and the surface heats up. Now imagine that the temperature had dropped to 0.5 degrees Celsius during the storm. In this case, the precipitation would fall as snow. After the storm passed and the sun came out, the surface would be covered with a sparkling white cover with 80 to 90% albedo. Most of the incoming solar radiation would reflect back into the atmosphere and the surface would remain much cooler. If the surface temperature did rise above freezing, the snow would have to melt before the ground temperature would rise. But snow has a very high latent heat. It takes a lot of energy to melt the snow without raising the temperature at all. In this example, a seemingly insignificant 1 degree initial temperature difference during a storm would cause a much larger temperature difference when the sun came out after the storm. This type of threshold mechanism is very important in weather and climate and will be discussed in chapters 19 and 20. Chapter 19, Moisture, Clouds, and Weather. Moisture in air precipitation occurs only when there is moisture in the air. Therefore, to understand precipitation, we must first understand how moisture collects in the atmosphere and how it behaves. Humidity. When water boils on a stove, a steamy mist rises above the pan and then disappears into the air. The water molecules have not been lost, they have simply become invisible. In the pan, water is liquid, and in the mist above, the water exists as tiny droplets. These droplets then evaporate, and the invisible water vapor mixes with air. Water also evaporates into air from the seas, streams, lakes, and soil. Winds then distribute this moisture throughout the atmosphere. Thus, all air contains some water vapor, even over the driest deserts. Humidity is the amount of water vapor in air. Absolute humidity is the mass of water vapor in a given volume of air, expressed in grams per cubic meter. Air can hold only a certain amount of water vapor, and warm air can hold more water vapor than cold air can. For example, air at 25 degrees Celsius can hold 23 gm of water vapor, but at 12 degrees Celsius, it can hold only half that quantity, 11.5 gm. Relative humidity is the amount of water vapor in air relative to the maximum it can hold at a given temperature. It is expressed as a percentage. If air contains half as much water vapor as it can hold, its relative humidity is 50%. Suppose that air at 25 degrees Celsius contains 11.5 gm of water vapor. Since air at that temperature can hold 23 gm, it is carrying half of its maximum, and the relative humidity is 11.5 g 23 g 100 equals 50%. Now let us take some of this air and cool it without adding or removing any water vapor. Because cold air holds less water vapor than warm air holds, the relative humidity increases even though the amount of water vapor remains constant. If the air cools to 12 degrees Celsius, and it still contains 11.5 gm, the relative humidity reaches 100% because air at that temperature can hold only 11.5 gm. When relative humidity reaches 100%, the air is saturated. The temperature at which saturation occurs, 12 degrees Celsius in this example, is the dew point. If saturated air cools below the dew point, some of the water vapor may condense into liquid droplets, although, as discussed next, under special conditions in the atmosphere, the relative humidity can rise above 100%. Supersaturation and supercooling. When the relative humidity reaches 100%, water vapor condenses quickly onto solid surfaces such as rocks, soil, and airborne particles. Airborne particles such as dust, smoke, and pollen are abundant in the lower atmosphere. Consequently, water vapor may condense easily at the dew point in the lower atmosphere, and there the relative humidity rarely exceeds 100%. However, in the clear, particulate-free air high in the troposphere, condensation occurs so slowly that for all practical purposes it does not happen. As a result, the air commonly cools below its dew point but water remains as vapor. In that case, the relative humidity rises above 100%, and the air reaches a point of supersaturation. Similarly, liquid water does not always freeze at its freezing point. Small droplets can remain liquid in a cloud even when the temperature is 40 degrees Celsius. Such water has undergone supercooling, cooling, and condensation. Moisture condenses to form water droplets or ice crystals when moist air cools below its dew point. Clouds and fog are visible concentrations of this airborne water and ice. 3. Atmospheric processes cool air to its dew point and cause condensation. Air cools when it loses heat by radiation. Air cools by contact with a cool surface such as water, ice, rock, soil, or vegetation. Air cools when it rises. Radiation cooling as described in Chapter 18. The atmosphere, rocks, soil, and water absorb the sun's heat during the day and then radiate some of this heat back out toward space at night. As a result of heat lost by radiation, air, land, and water become cooler at night, and condensation may occur. Contact cooling, dew and frost. You can observe condensation on a cool surface with a simple demonstration. Heat water on a stove until it boils and then hold a cool drinking glass in the clear air just above the steam. Water droplets will condense on the surface of the glass because the glass cools the hot, moist air to its dew point. The same effect occurs in a house on a cold day. Water droplets or ice crystals appear on windows as warm, moist, indoor air cools on the glass. In some regions, the air on a typical summer evening is warm and humid. After the sun sets, plants, houses, windows, and most other objects lose heat by radiation and therefore become cool. During the night, water vapor condenses on the cool objects. This condensation is called dew. If the dew point is below freezing, frost forms. Frost is not frozen dew, but ice crystals formed directly from vapor. Cooling of rising air. Radiation and contact cooling close to Earth's surface form dew, frost, and some types of fog. However, clouds and precipitation normally form at higher elevations where the air is not cooled by direct contact with the ground. Almost all cloud formation and precipitation occur when air cools as it rises. Work and heat are both forms of energy. Work can be converted to heat or heat can be converted to work, but energy is never lost. If you pump up a bicycle tire, you are performing work to compress the air. This energy is not lost, much of it converts to heat. Therefore, both the pump and the newly filled tire feel warm. Conversely, if you puncture a tire, the air rushes out. It must perform work to expand, so the air rushing from a punctured tire cools. Variations in temperature caused by compression or expansion of gas are called adiabatic temperature changes. Adiabatic means without gain or loss of heat. During adiabatic warming, air warms up because work is done on it, not because heat is added. During adiabatic cooling, air cools because it performs work, not because heat is removed. Air pressure decreases with elevation. When dense surface air rises, it expands because the atmosphere around it is now of lower density, just as air expands when it rushes out of a punctured tire. Rising air performs work to expand, and therefore it cools adiabatically. Dry air cools by 10 degrees Celsius for every 1,000 meters it rises. This cooling rate is called the dry adiabatic lapse rate. Thus, if dry air were to rise from sea level to 9,000 meters, it would cool by 90 degrees Celsius. Almost all air contains some water vapor. As moist air rises and cools adiabatically, its temperature may eventually decrease to the dew point. At the dew point, moisture may condense as droplets, and a cloud forms. But recall that condensing vapor releases latent heat. As the air rises through the cloud, its temperature now is affected by two opposing processes. It cools adiabatically, but at the same time it is heated by the latent heat released by condensation. However, the warming caused by latent heat is generally less than the amount of adiabatic cooling. The net result is that the rising air continues to cool, but more slowly than at the dry adiabatic lapse rate. The wet adiabatic lapse rate is the cooling rate after condensation has begun. It varies from 5 degrees Celsius for every 1,000 meters it rises. For air with a high moisture content to 9 degrees Celsius for every 1,000 meters it rises for relatively dry air, figure 19. 4. Thus, once clouds start to form, rising air no longer cools as rapidly as it did lower in the atmosphere. Rising air cools at the dry adiabatic lapse rate until it cools to its dew point and condensation begins. Then, as it continues to rise, it cools at the lesser, wet adiabatic. Lapse rate as condensation continues. In contrast, sinking air becomes warmer because of adiabatic compression. Warm air can hold more water vapor than cool air can. Consequently, water does not condense from sinking, warming air, and the latent heat of condensation does not affect the rate of temperature rise. As a result, sinking air always becomes warmer at the dry adiabatic rate. Rising air and precipitation. To summarize, when moist air rises, it cools and forms clouds. 3 mechanisms cause air to rise: orographic lifting, frontal wedging, and convection, convergence. Orographic lifting: when air flows over mountains, it is forced to rise by a mechanism called orographic lifting. This rising air frequently causes rain or snow over the mountains, as will be explained in section on how the Earth's surface features affect weather. Frontal wedging: a moving mass of cool, dense air may encounter a mass of warm, less dense air. When this occurs, the cool, denser air slides under the warm air mass, forcing the warm air upward to create a weather front. This process is called frontal wedging. We will discuss weather fronts in more detail in sections on fronts and frontal weather, thunderstorms, and tornadoes and tropical cyclones. Convection, convergence. Recall that convection is the upward, downward, and horizontal flow of fluids in response to heating and cooling. If one portion of the atmosphere becomes warmer than the surrounding air, the warm air expands, becomes less dense, and rises. Thus, a hot air balloon rises because it contains air that is warmer and less dense than the air around it. If the sun heats one parcel of air near Earth's surface to a warmer temperature than that of surrounding air, the warm air will rise, just as the hot air balloon rises. Convective processes and clouds. On some days, clouds hang low over the land and obscure nearby hills. At other times, clouds float high in the sky, well above the mountain peaks. What factors determine the height and shape of a cloud? Recall that air is generally warmest at Earth's surface and cools with elevation throughout the troposphere. The rate at which air that is neither rising nor falling cools with elevation is called the normal lapse rate. The average normal lapse rate is 6 degrees Celsius for every 1,000 meters of elevation, and thus is less than the dry adiabatic lapse rate. However, the normal lapse rate is variable. Typically, it is greatest near Earth's surface and decreases with altitude. The normal lapse rate also varies with latitude, the time of day, and the seasons. It is important to note that the normal lapse rate is simply the vertical temperature structure of the atmosphere. In contrast, rising air cools because of adiabatic cooling. Figure 19.6 shows 2 rising, warm air masses, one consisting of dry air and the other of moist air. The central part of the figure shows that the normal lapse rate is the same for both air masses. The temperature of the atmosphere decreases rapidly in the first few thousand meters and then more slowly with increasing elevation. However, the 2 air masses behave differently because of their different moisture contents. The dry air mass rises and cools at the dry adiabatic lapse rate of 10 degrees Celsius 1000 m. As a result, in this example, the mass's temperature and density become equal to that of surrounding air at an elevation of 3,000 meters. Because the density of the rising air is the same as that of the surrounding air, the rising air is no longer buoyant, and it stops rising. No clouds form because the air has not cooled to its dew point. In Figure 19. 6b, the rising moist air initially cools at the dry adiabatic rate of 10 degrees Celsius 1000 m, but only until the air cools to its dew point. At an elevation of 1,000 meters. At that point, moisture begins to condense, and clouds form. But the condensing moisture releases latent heat of condensation. This additional heat causes the rising air to cool more slowly, at the wet adiabatic rate of 5 degrees Celsius 1000 m. As a result, the rising air remains warmer and more buoyant than surrounding air, and it continues to rise for thousands of meters, creating a towering, billowing cloud with the potential for heavy precipitation. In simple terms, warm, moist air is unstable air because it rises rapidly, forming towering clouds and heavy rainfall. Also, as shown in Figure 19.5c, air rushes along the ground to replace the rising air, thus generating surface winds. Most of us have experienced a violent thunderstorm on a hot, summer day. Puffy clouds seem to appear out of nowhere in a blue sky. These clouds grow vertically and darken as the afternoon progresses. Suddenly, gusts of wind race across the land, and shortly thereafter, heavy rain falls. These events, to be described in more detail in section on fronts and frontal weather, are all caused by unstable, rising, moist air. In contrast, warm, dry air doesn't rise rapidly, doesn't ascend to high elevations, and doesn't lead to cloud formation and precipitation. Thus warm, dry air is said to be stable air. Yet, keep in mind that convection is only one of the three processes that leads to rising air. Orographic lifting and frontal wedging also lead to rising air. Cloud formation and rain, as explained earlier. Types of clouds. Even a casual observer of the daily weather will notice that clouds are quite different from day to day. Different meteorological conditions create the various cloud types and, in turn, a look at the clouds can provide useful information about the daily weather. Cirrus clouds are wispy clouds that look like hair blowing in the wind or feathers floating across the sky. Cirrus clouds form at high altitudes, 6,000 to 15,000 meters. The air is so cold at these elevations that cirrus clouds are composed of ice crystals rather than water droplets. High winds aloft blow them out into long, gently curved streamers. Stratus clouds are horizontally layered, sheet-like clouds. They form when condensation occurs at the same elevation at which air stops rising and the clouds spread out into a broad sheet. Stratus clouds form the dark, dull gray, overcast skies that may persist for days and bring steady rain. Cumulus clouds are fluffy, white clouds that typically display flat bottoms and billowy tops. On a hot, summer day, the top of a cumulus cloud may rise 10 kilometers or more above its base in cauliflower-like masses. The base of the cloud forms at the altitude at which the rising air cools to its dew point and condensation starts. However, in this situation the rising air remains warmer than the surrounding air and therefore continues to rise. As it rises, more vapor condenses, forming the billowing columns. Other types of clouds are named by combining these three basic terms. Stratocumulus clouds are low, sheet-like clouds with some vertical structure. The term nimbo refers to a cloud that precipitates, thus a cumulonimbus cloud is a towering rain cloud. If you see one, you should seek shelter, because cumulonimbus clouds commonly produce intense rain, thunder, lightning, and sometimes hail. A nimbostratus cloud is a stratus cloud from which rain or snow falls. Other prefixes are also added to cloud names. For example, alti is derived from the Latin root altus, meaning high. An altostratus cloud is simply a high stratus cloud. Why does rain fall from some clouds, whereas other clouds float across a blue sky on a sunny day and produce no rain? The droplets in a cloud are small, about 0.01 millimeter in diameter. In still air, such a droplet would require 48 hours to fall from a cloud 1,000 meters above Earth. But these tiny droplets never reach Earth because they evaporate faster than they fall. If the air temperature in a cloud is above freezing, the tiny droplets may collide and coalesce. You can observe similar behavior in droplets sliding down a window pane on a rainy day. If two droplets collide, they merge to become one large drop. If the droplets in a cloud grow large enough, they fall as drizzle or light rain. About 1 million cloud droplets must combine to form an average-size raindrop. In many clouds, however, water vapor initially forms ice crystals rather than condensing as tiny droplets of supercooled water. Part of the reason for this is that the temperature in clouds is commonly below freezing, but another factor also favors ice formation. At temperatures near or below freezing, air that is slightly undersaturated with respect to water is slightly supersaturated with respect to ice. For example, if the relative humidity of air is 95% with respect to water, it is about 105% with respect to ice. Thus, as air cools toward its dew point, all the vapor forms ice crystals rather than supercooled water droplets. The tiny ice crystals then grow larger as more water vapor condenses on them, until they are large enough to fall. The ice then melts to form raindrops as it falls through warmer layers of air. If you have ever been caught in a thunderstorm, you may remember raindrops large enough to be painful as they struck your face or hands. Recall that a cumulus cloud forms from rising air and that its top may be several kilometers above its base. The temperature in the upper part of the cloud is commonly below freezing. As a result, ice crystals form and begin to fall. Condensation continues as the crystal falls through the towering cloud, and the crystal grows. If the lower atmosphere is warm enough, the ice melts before it reaches the surface. Raindrops formed in this manner may be 3 to 5 millimeters in diameter, large enough to hurt when they hit. Snow, sleet, and glaze. As explained previously, when the temperature in a cloud is below freezing, the cloud is composed of ice crystals rather than water droplets. If the temperature near the ground is also below freezing, the crystals remain frozen and fall as snow. In contrast, if raindrops form in a warm cloud and fall through a layer of cold air at lower elevation, the drops freeze and fall as small spheres of ice called sleet. Sometimes the freezing zone near the ground is so thin that raindrops do not have time to freeze before they reach Earth. However, when they land on sub-freezing surfaces, they form a coating of ice called glaze. Glaze can be heavy enough to break tree limbs and electrical transmission lines. It also coats highways with a dangerous icy veneer. In the winter of 1997-1998, a sleet and glaze storm in eastern Canada and the northeastern United States caused billions of dollars in damage. The ice damaged so many electric lines and power poles that many people were without electricity for a few weeks. Hail. Occasionally, precipitation takes the form of very large ice globules called hail. Hailstones vary from 5 mm in diameter to a record 14 cm in diameter. That record breaker weighed 765 grams and fell in Kansas. A 500-gram hailstone crashing to Earth at 160 km/h can shatter windows, dent car roofs, and kill people and livestock. Even small hailstones can damage crops. Hail falls only from cumulonimbus clouds. Because cumulonimbus clouds form in columns with distinct boundaries, hailstorms occur in local, well-defined areas. Thus, one farmer may lose an entire crop while a neighbor is unaffected. A hailstone consists of ice in concentric shells, like the layers of an onion. Two mechanisms have been proposed for their formation. In one, turbulent winds blow falling ice crystals back upward in the cloud. New layers of ice accumulate as additional vapor condenses on the recirculating ice grain. An individual particle may rise and fall several times until it grows so large and heavy that it drops out of the cloud. In the second mechanism, hailstones form in a single pass through the cloud. During their descent, supercooled water freezes onto the ice crystals. The layering develops because different temperatures and amounts of supercooled water exist in different portions of the cloud, and each layer forms in a different part of the cloud. Fog. Fog is a cloud that forms at or very close to ground level, although most fog forms by processes different from those that create higher-level clouds. Advection fog occurs when warm, moist air from the sea blows onto cooler land. The air cools to its dew point, and water vapor condenses at ground level. San Francisco and Seattle, as well as Vancouver, British Columbia, all experience foggy winters as warm, moist air from the Pacific Ocean is cooled first by the cold California current and then by land. The foggiest location in the United States is Cape Disappointment, Washington, on the Pacific Ocean at the mouth of the Columbia River, where visibility is obscured by fog 29% of the time. Radiation fog occurs when Earth's surface and air near the surface cool by radiation during the night. Water vapor condenses as fog when the air cools below its dew point. Often the cool, dense, foggy air settles into valleys. If you are driving late at night in hilly terrain, beware, because a sudden dip in the roadway may lead you into a thick fog where visibility is low. A ground fog of this type typically burns off in the morning. The rising sun warms the land or water surface which, in turn, warms the low-lying air. As the air becomes warmer, its capacity to hold water vapor increases, and the fog droplets evaporate. Radiation fog is particularly common in areas where the air is polluted because water vapor condenses readily on the tiny particles suspended in the air. Recall that vaporization of water absorbs heat and, therefore, cools both the surface and the surrounding air. In addition, vaporization adds moisture to the air. The cooling and the addition of moisture combine to form conditions conducive to fog. Evaporation fog occurs when air is cooled by evaporation from a body of water, commonly a lake or river. Evaporation fogs are common in late fall and early winter, when the air has become cool but the water is still warm. The water evaporates, but the vapor cools and condenses to fog almost immediately upon contact with the cold air. Upslope fog occurs when air cools as it rises along a land surface. Upslope fogs occur both on gradually sloping plains and on steep mountains. For example, the Great Plains rise from sea level at the Mississippi Delta to 1,500 meters at the Rocky Mountain front. When humid air moves northwest from the Gulf of Mexico toward the Rockies, it rises and cools adiabatically to form upslope fog. The rapid rise at the mountain front also forms fog. Pressure and wind. Warm air is less dense than cold air. Thus, warm air exerts a relatively low atmospheric pressure and cold air exerts a relatively high atmospheric pressure. Warm air rises because it is less dense than the surrounding cool air. Air rises slowly above a typical low-pressure region, at a rate of about 1 km per day. In contrast, if air in the upper atmosphere cools, it becomes denser than the air beneath it and sinks. Air must flow inward over Earth's surface toward a low-pressure region to replace a rising air mass. But a sinking air mass displaces surface air, pushing it outward from a high-pressure region. Thus, vertical airflow in both high and low-pressure regions is accompanied by horizontal airflow, called wind. Winds near Earth's surface always flow away from a region of high pressure and toward a low-pressure region. Ultimately, all wind is caused by the pressure differences resulting from unequal heating of Earth's atmosphere. Pressure gradient wind blows in response to differences in pressure. Imagine that you are sitting in a room and the air is still. Now you open a can of vacuum-packed coffee and hear the hissing as air rushes into the can. Because the pressure in the room is higher than that inside the coffee can, wind blows from the room into the can. But if you blow up a balloon, the air inside the balloon is at higher pressure than the air in the room. When the balloon is punctured, wind blows from the high-pressure zone of the balloon into the lower-pressure zone of the room. Wind speed is determined by the magnitude of the pressure difference over distance, called the pressure gradient. Thus, wind blows rapidly if a large pressure difference exists over a short distance. A steep pressure gradient is analogous to a steep hill. Just as a ball rolls quickly down a steep hill, wind flows rapidly across a steep pressure gradient. To create a pressure gradient map, air pressure is measured at hundreds of different weather stations. Points of equal pressure are connected by map lines called isobars. A steep pressure gradient is shown by closely spaced isobars, whereas a weak pressure gradient is indicated by widely spaced isobars. Pressure gradients change daily, or sometimes hourly, as high and low pressure zones move. Therefore, maps are updated frequently. Coriolis effect recall. From Chapter 16 that the Coriolis effect, caused by Earth's spin, deflects ocean currents. The Coriolis effect similarly deflects winds. In the northern hemisphere, wind is deflected toward the right, and in the southern hemisphere, to the left. The Coriolis effect alters wind direction but not its speed. Friction. Rising and falling air generates wind both along Earth's surface and at higher elevations. Surface winds are affected by friction with Earth's surface, whereas high-altitude winds are not. As a result, wind speed normally increases with elevation. This effect was first noted during World War II. On November 24, 1944, U.S. bombers were approaching Tokyo for the first mass bombing of the Japanese capital. Flying between 8,000 and 10,000 meters, the pilots suddenly found themselves roaring past landmarks 140 kilometers per hour faster than the theoretical top speed of their airplanes. Amid the confusion, most of the bombs missed their targets, and the mission was a military failure. However, this experience introduced meteorologists to jet streams, narrow bands of high-altitude wind. The jet stream in the northern hemisphere flows from west to east at speeds between 120 and 240 kilometers per hour. As a comparison, surface winds attain such velocities only in hurricanes and tornadoes. Airplane pilots traveling from Los Angeles to New York fly with the jet stream to gain speed and save fuel, whereas pilots moving from east to west try to avoid it. Jet stream influence on weather and climate will be discussed again later in this chapter and in more detail in Chapter 20. Cyclones and anticyclones. Figure 19.16a shows the movement of air in the northern hemisphere as it converges toward a low-pressure area. If Earth did not spin, wind would flow directly across the isobars, as shown by the black arrows. However, Earth does spin, and the Coriolis effect deflects wind to the right, as shown by the small blue arrows. This rightward deflection creates a counterclockwise vortex near the center of the low-pressure region, as shown by the large, magenta arrows. In the southern hemisphere, the direction is clockwise. Such a low-pressure region with its accompanying surface wind is called a cyclone. In this usage, cyclone means a system of inwardly directed rotating winds, not the violent storms that are sometimes called cyclones, hurricanes, or typhoons. The opposite mechanism forms an anticyclone around a high-pressure region. When descending air reaches the surface, it spreads out in all directions. In the northern hemisphere, the Coriolis effect deflects the diverging winds of an anticyclone to the right, forming a pinwheel pattern, with the wind spiraling clockwise. In the southern hemisphere, the Coriolis effect deflects winds leftward and creates a counterclockwise spiral. Pressure changes and weather. As explained earlier, wind blows in response to any difference in pressure. However, low pressure generally brings clouds and precipitation with the wind, and sunny days predominate during high pressure. To understand this distinction, recall that warm air is less dense than cold air. If warm and cold air are in contact, the less dense, and therefore buoyant, warm air rises. Rising air forms a region of low pressure. But rising air also cools adiabatically. If the cooling is sufficient, clouds form and rain or snow may fall. Thus, low barometric pressure is an indication of wet weather. Alternatively, when cool air sinks, it is compressed and the pressure rises. In addition, sinking air is heated adiabatically. Because warm air can hold more water vapor than cold air can, the sinking air absorbs moisture, and thus clouds generally do not form over a high-pressure region. Thus, fair, dry weather generally accompanies high-pressure fronts. And frontal weather. An air mass is a large body of air with approximately uniform temperature and humidity at any given altitude. Typically, an air mass is 1,500 kilometers or more across and several kilometers thick. Because air acquires both heat and moisture from Earth's surface, an air mass is classified by its place of origin. Temperature can be either polar or tropical. Maritime air originates over water and has high moisture content, whereas continental air has low moisture content. Air masses move and collide. The boundary between a warmer air mass and a cooler one is a front. The term was first used during World War I because weather systems were considered analogous to armies that advance and clash along battle lines. When two air masses collide, each may retain its integrity for days before the two mix. During a collision, one of the air masses is forced to rise, which often results in cloudiness and precipitation. Frontal weather patterns are determined by the types of air masses that collide and their relative speeds and directions. The symbols commonly used on weather maps to describe fronts are shown in Figure 19.18. Warm fronts and cold fronts. Fronts are classified by weather. A warm air mass moves toward a stationary cold mass, or vice versa. A warm front forms when moving warm air collides with a stationary or slower-moving cold air mass. A cold front forms when moving cold air collides with stationary or slower-moving warm air. In a warm front, the moving warm air rises over the denser cold air as the two masses collide. The rising warm air cools adiabatically and the cooling generates clouds and precipitation. Precipitation is generally light because the air rises slowly along the gently sloping frontal boundary. Figure 19.19 shows that a characteristic sequence of clouds accompanies a warm front. High, wispy cirrus and cirrostratus clouds develop near the leading edge of the rising warm air. These high clouds commonly precede a storm. They form as much as 1,000 kilometers ahead of an advancing band of precipitation that falls from thick, low-lying nimbostratus and stratus clouds near the trailing edge of the front. The cloudy weather may last for several days because of the gentle slope and broad extent of the frontal boundary. A cold front forms when faster-moving cold air overtakes and displaces warm air. The dense cold air forms a blunt wedge and pushes under the warmer air, Figure 19.20. Thus, the leading edge of a cold front is much steeper than that of a warm front. The steep contact between the two air masses causes the warm air to rise rapidly, creating a narrow band of violent weather commonly accompanied by cumulus and cumulonimbus clouds. The storm system may be only 25 to 100 kilometers wide, but within this zone downpours, thunderstorms, and violent winds are common. Occluded front. An occluded front forms when a faster-moving cold air mass traps a warm air mass against a second mass of cold air. Thus, the warm air mass becomes trapped between two colder air masses. The faster-moving cold air mass then slides beneath the warm air, lifting it completely off the ground. Precipitation occurs along both frontal boundaries, combining the narrow band of heavy precipitation of a cold front with the wider band of lighter precipitation of a warm front. The net result is a large zone of inclement weather. A storm of this type is commonly short-lived, because the warm air mass is cut off from its supply of moisture evaporating from Earth's surface. Stationary front. A stationary front occurs along the boundary between two stationary air masses. Under these conditions, the front can remain over an area for several days. Warm air rises, forming conditions similar to those in a warm front. As a result, rain, drizzle, and fog may occur. The life cycle of a mid-latitude cyclone, as you learned in section on pressure and wind. Cyclone is a low-pressure system with rotating winds. Most cyclones in the middle latitudes of the northern hemisphere develop along a front between polar and tropical air masses. The storm often starts with winds blowing in opposite directions along a stationary front between the two air masses. In the figure, a warm air mass was moving northward and was deflected to the east by the Coriolis effect. At the same time, a cold air mass traveling southward was deflected to the west. In figure 19.22b, the cold polar air continues to push southward, creating a cold front and lifting the warm air off the ground. Then, some small disturbance, a topographic feature such as a mountain range, airflow from a local storm, or perhaps a local temperature variation, deforms the straight frontal boundary, forming a wave-like kink in the front. Once the kink forms, the winds on both sides are deflected to strike the front at an angle. Thus, a warm front forms to the east and a cold front forms to the west. Rising warm air then forms a low-pressure region near the kink. In the northern hemisphere, the Coriolis effect causes the winds to circulate counterclockwise around the kink, as explained in section on pressure and wind. To the west, the cold front advances southward, and to the east, the warm front advances northward. At the same time, rain or snow falls from the rising warm air. Over a period of 1 to 3 days, the air rushing into the low-pressure region equalizes pressure differences, and the storm dissipates. Many of the pinwheel-shaped storms seen on weather maps are cyclones of this type. In North America, the jet stream and other prevailing, upper-level, westerly winds generally move cyclones from west to east along the same paths, called storm tracks. How the Earth's surface features affect weather. Earth's surface features, including mountain ranges, rainforests, proximity to the sea, and uneven heating and cooling of continents, can create conditions that affect the weather of a region. Mountain ranges and rain shadow deserts. As we described in section on rising air and precipitation, air rises in a process called orographic lifting when it flows over a mountain range. As the air rises, it cools adiabatically, and water vapor may condense into clouds that produce rain or snow. These conditions create abundant precipitation on the windward side and the crest of the range. When the air passes over the crest onto the leeward side, it sinks. This air has already lost much of its moisture. In addition, it warms adiabatically as it falls, absorbing moisture and creating a rain shadow desert on the leeward side of the range. For example, Death Valley, California, is a rain shadow desert and receives only 5 centimeters of rain a year, while the nearby west slope of the Sierra Nevada receives 178 centimeters of rain a year. Forests and weather. Recall that atmospheric moisture condenses when moist air cools below its dew point. Forests cool the air. Large quantities of water evaporate from leaf surfaces in the process called transpiration, and evaporation cools the surrounding air. In addition, forests shade the soil from the hot sun, and tree roots and litter retain moisture. In an open clearing, rainwater evaporates quickly after a storm or runs off the surface. But forest soils remain moist long after the rain dissipates. Evaporation from soil litter combines with transpiration cooling from leaf surfaces to maintain relatively cool temperatures during times when there is no rain. In yet another feedback mechanism, forests cool the air. Cool air promotes rainfall. Rainfall supports forests. In today's tropical rainforests, local rainfall has decreased by as much as 50% when the forests were cut and replaced by farmland or pasture. When the rainfall decreases, wildfires ravage the boundary between the logged area and the remaining virgin forests. More forest is destroyed, establishing a negative feedback mechanism of increasing drought, fire, and forest loss. Sea and land breezes. Anyone who has lived near an ocean or large lake would have encountered winds blowing from water to land and from land to water. Sea and land breezes are caused by uneven heating and cooling of land and water. Recall that land surfaces heat up faster than adjacent bodies of water and cool more quickly. If land and sea are at nearly the same temperature on a summer morning, during the day the land warms and heats the air above it. Hot air then rises over the land, producing a local low-pressure area. Cooler air from the sea flows inland to replace the rising air. Thus, on a hot sunny day, winds generally blow from the sea onto land. The rising air is good for flying kites or hang gliding but often brings afternoon thunderstorms. At night the reverse process occurs. The land cools faster than the sea, and descending air creates a local high-pressure area over the land. Then the winds reverse, and breezes blow from the shore out toward the sea. Monsoons. A monsoon is a seasonal wind and weather system caused by uneven heating and cooling of continents and adjacent oceans. Just as sea and land breezes reverse direction with day and night, monsoons reverse direction with the seasons. In the summertime, the continents become warmer than the sea. Warm air rises over land, creating a large low-pressure area and drawing moisture-laden maritime air inland. When the moist air rises as it flows over the land, clouds form and heavy monsoon rains fall. In winter, the process is reversed. The land cools below the sea temperature, and as a result air descends over land, producing dry, continental, high pressure. At the same time, air rises over the ocean and the prevailing winds blow from land to sea. More than half of the inhabitants of Earth depend on monsoons because the predictable, heavy, summer rains bring water to the fields of Africa and Asia. If the monsoons fail to arrive, crops cannot grow and people starve. Thunderstorms. An estimated 16 million thunderstorms occur every year, and at any given moment, about 27,000 thunderstorms are in progress over different parts of Earth. A single bolt of lightning can involve several 100 million volts of energy and for a few seconds produces as much power as a nuclear power plant. It heats the surrounding air to 25,000 degrees Celsius. Or more, much hotter than the surface of the Sunday. The heated air expands instantaneously to create a shock wave that we hear as thunder. Despite their violence, thunderstorms are local systems, often too small to be included on national weather maps. A typical thunderstorm forms and then dissipates in a few hours and covers from about 10 to a few hundred square kilometers. It is not unusual to stand on a hilltop in the sunshine and watch rain squalls and lightning a few kilometers away. All thunderstorms develop when warm, moist air rises, forming cumulus clouds that develop into towering cumulonimbus clouds. Different conditions cause these local regions of rising air. 1. Wind convergence. Central Florida is the most active thunderstorm region in the United States. As the subtropical sun heats the Florida peninsula, rising air draws moist air from its both east and west coasts. Where the two air masses converge, the moist air rises rapidly to create a thunderstorm. Thunderstorms also occur in other environments where moist air masses converge. 2. Convection. Thunderstorms also form in continental interiors during the spring or summer, when afternoon sunshine heats the ground and generates cells of rising, moist air. 3. Orographic lifting. Moist air rises as it flows over hills and mountain ranges, commonly generating mountain thunderstorms. 4. Frontal thunderstorms. Thunderstorms commonly occur along frontal boundaries, particularly at cold fronts. Lightning is an intense discharge of electricity that occurs when the buildup of static electricity overwhelms the insulating properties of air. If you walk across a carpet on a dry day, the friction between your feet and the rug shears electrons off the atoms on the rug. The electrons migrate into your body and concentrate there. If you then touch a metal doorknob, a spark consisting of many electrons jumps from your finger to the metal knob. In 1752, Benjamin Franklin showed that lightning is an electrical spark. He suggested that charges separate within cumulonimbus clouds and build until a bolt of lightning jumps from the cloud. In the more than 250 years since Franklin, atmospheric physicists have been unable to agree upon the exact mechanism of lightning. According to one hypothesis, friction between the intense winds and moving ice crystals in a cumulonimbus cloud generates both positive and negative electrical charges in the cloud, and the two types of charges become physically separated. The positive charges tend to accumulate in the upper portion of the cloud, and the negative charges build up in the lower reaches of the cloud. When enough charge accumulates, the electrical potential exceeds the insulating properties of air, and a spark jumps from the cloud to the ground, from the ground to the cloud, or from one cloud to another. Another hypothesis suggests that cosmic rays bombarding the cloud from outer space produce ions at the top of the cloud. Other ions form on the ground as winds blow over Earth's surface. The electrical discharge occurs when the potential difference between the two groups of electrical charges exceeds the insulating properties of air. Perhaps neither hypothesis is entirely correct, and some combination of the mechanisms causes lightning. Tornadoes and tropical cyclones. Tornadoes and tropical cyclones are both intense low-pressure centers. Strong winds follow the steep pressure gradients and spiral inward toward a central column of rising air. Tornadoes. A tornado is a small, short-lived, funnel-shaped storm that protrudes from the base of a cumulonimbus cloud. The base of the funnel can be from 2 meters to 3 kilometers in diameter. Some tornadoes remain suspended in air while others touch the ground. After a tornado touches ground, it may travel for a few meters to a few hundred kilometers across the surface. The funnel travels at 40 to 65 kilometers per hour, and in some cases as much as 110 kilometers per hour, but the spiraling winds within the funnel are much faster. Few direct measurements have been made of pressure and wind speed inside a tornado. However, we know that a large pressure difference occurs over a very short distance. Meteorologists estimate that winds in tornadoes may reach 500 kilometers per hour or greater. These winds rush into the narrow, low-pressure zone and then spiral upward. After a few seconds to a few hours, the tornado lifts off the ground and dissipates. Tornadoes are the most violent of all storms. One tornado in 1910 lifted a team of horses and then deposited it, unhurt, several hundred meters away. They were lucky. In the past, an average of 120 Americans were killed every year by these storms, and property damage costs millions of dollars. The death toll has decreased in recent years because effective warning systems allow people to seek shelter, but the property damage has continued to increase. Tornado winds can lift the roof off a house and then flatten the walls. Flying debris kills people and livestock caught in the open. Even so, the total destruction from tornadoes is not as great as that from hurricanes. Because the path of a tornado is narrow and its duration is short. Although tornadoes can occur anywhere in the world, 75% of the world's twisters concentrate in the Great Plains, east of the Rocky Mountains. Approximately 700 to 1,000 tornadoes occur in the United States each year. They frequently form in the spring or early summer. At that time, continental polar air from Canada collides with maritime tropical air from the Gulf of Mexico. As explained previously, these conditions commonly create thunderstorms. Meteorologists cannot explain why most thunderstorms dissipate harmlessly but a few develop tornadoes. However, one fact is apparent: tornadoes are most likely to occur when large differences in temperature and moisture exist between the two air masses and the boundary between them is sharp. Tropical cyclones. A tropical cyclone or tropical storm is less intense than a tornado but much larger and longer-lived. Tropical cyclones are circular disturbances that average 600 kilometers in diameter and persist for days or weeks. If the wind exceeds 120 kilometers per hour, a tropical cyclone is called a hurricane in North America and the Caribbean, a typhoon in the Western Pacific, and a cyclone in the Indian Ocean. Intense low pressure in the center of a hurricane can generate wind as strong as 300 kilometers per hour. The low atmospheric pressure created by a tropical cyclone can raise the sea surface by several meters. Often, as a tropical cyclone strikes shore, strong onshore winds combine with the abnormally high water level created by low pressure to create a storm surge that floods coastal areas. In 2005, during Hurricane Katrina, sea level rose about 8.5 meters above normal on the Gulf Coast as a result of a storm surge. Tropical cyclones form only over warm oceans, never over cold oceans or land. Thus, moist, warm air is crucial to the development of this type of storm. A mid-latitude cyclone develops when a small disturbance produces a wave-like kink in a previously linear front. A similar mechanism initiates a tropical cyclone. In late summer, the sun warms tropical air. The rising hot air creates a belt of low pressure that encircles the globe over the tropics. In addition, many local low-pressure disturbances move across the tropical oceans at this time of year. If a local disturbance intersects the global tropical low, it creates a bulge in the isobars. Winds are deflected by the bulge and, directed by the Coriolis effect, begin to spiral inward. Warm, moist air rises from the low. Water vapor condenses from the rising air, and the latent heat warms the air further, which causes even more air to rise. As the low pressure becomes more intense, strong surface winds blow inward to replace the rising air. This surface air also rises, and more condensation and precipitation occur. But the additional condensation releases more heat, which continues to add energy to the storm. The center of the storm is a region of vertical airflow, called the eye. In the outer, and larger, part of the eye, the air that has been rushing inward spirals upward. In the inner eye, air sinks. Thus, the horizontal wind speed in the eye is reduced to near zero. Survivors who have been in the eye of a hurricane report an eerie calm. Rain stops, and the sun may even shine weakly through scattered clouds. But this is only a momentary reprieve. A typical eye is only 20 kilometers in diameter, and after it passes, the hurricane rages again in full intensity. Thus, a hurricane is powered by a classic feedback mechanism. The low-pressure storm causes condensation. Condensation releases heat. Heat powers the continued low pressure. The entire storm is pushed by prevailing winds, and its path is deflected by the Coriolis effect. A hurricane usually dissipates only after it reaches land or passes over colder water because the supply of moist, warm air is cut off. Condensing water vapor in a single tropical cyclone releases as much latent heat energy as that produced by all the electric generators in the United States in a 6-month period. The numerical category of tropical cyclones is based on a rating scheme called the Saffir-Simpson scale, after its developers. This scale, commonly mentioned in weather reports, rates the damage potential of a hurricane or other tropical storm, and typical values of atmospheric pressure, wind speed, and height of storm surge associated with storms of increasing intensity. Hurricane Katrina scope of the disaster. Hurricane Katrina formed in the South Atlantic on August 23, 2005. Made landfall as a Category 1 hurricane just north of Miami, then crossed the Florida peninsula and grew to a Category 5 storm in the Gulf of Mexico with sustained winds of 280 km per hour. By the time it made a second landfall on the Mississippi Delta, Hurricane Katrina had diminished to a Category 34 storm, with winds hovering around 200 km per hour. Yet despite the reduced winds, Katrina quickly became the most costly and one of the deadliest natural disasters in U.S. history. Parts of New Orleans were flooded to the rooftops of houses. In addition, a record 8.5-meter storm surge inundated the New Orleans and Mississippi coastlines, flattening and flooding homes over 233,000 square kilometers, an area almost as large as the United Kingdom. Approximately 1.3 million people were driven from their homes.